Hey, listeners, before we get into this episode, I have some fantastic news. My new book, Developing Mathematical Reasoning, Avoiding the Trap of Algorithms, is coming out, and we are having a book launch webinar to celebrate. This book spans from kindergarten to 12th grade, explaining in detail how algorithms trap students and what we should be teaching instead.
Join us at this free book launch webinar and you'll learn what the traps of algorithms are, how to avoid them, and so much more. You don't want to miss it.
We'll go live on March 18th, 7 p.m. Central. Grab your spot at mathisfigureoutable.com/book-launch.
That's www.mathisfigureoutable.com/book-launch. We hope to see you there.
Hey, fellow mathers, welcome to the podcast where math is figure-outable. I'm Pam, a former mimicker turned mather.
And I'm Kim, a reasoner who now knows how to share her thinking with others. At Math is Figureoutable, we are on a mission to improve math teaching.
Because we know that algorithms are amazing human achievements, but y'all, they are not good teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than the problems are intended to develop.
In this podcast, we hope you teach mathing, building relationships with your students, and grappling with mathematical relationships.
Thanks for joining us to make math more figure-outable.
Hi
All right,
there.
let's dive in today because I'm super excited. So, you know that my brand new book is out, Developing Mathematical Reasoning, Avoiding the Trap of Algorithms.
Yes, ma'am.
So, Kim, today I am hoping that you're okay. If you're all right with it, let's talk about one of the major traps of the algorithms.
Yes.
And let's be honest. So let's be honest. That's not what I meant to say.
We're always honest, Pam.
We're always, yeah. Let's fine tune that.
Okay.
What I'm trying to say is, in the book, I outline major traps of many of the traditional algorithms that we teach in schools.
Yep.
But one of the things that I did was specifically outline that there are Oh, heavens.
Are you tired?
I'm going to take a breath. I have so many things happening in my head right now. It's like trying to parse them out. I outlined 3 traps that fit, I think, all algorithms. Yes. So pick a specific algorithm, and there are a lot of traps in that specific algorithm. Yep. But I think there's 3 main traps that kind of fit all the algorithms. Yes. So I'm super curious, y'all, if you can, what I propose today, Kim, is that we go through one of those traps kind of in detail.
Okay.
And I really want to invite our listening audience to think about any algorithm that is taught typically at your grade level in your subject, and think to yourself, this one, we're going to go over one today. Does this trap, do I find that in my particular algorithm? I've thought about as many of them as I can generate, but I'm really curious if you can think of one that maybe this trap doesn't fit for.
Okay.
I'm gonna bet not. This one's so important. All right, so Kim, the trap that I am inviting us to talk about today, we actually mention in the intro.
Okay.
And we mention in the intro because I say that mimicking step-by-step procedures can actually trap students into using less sophisticated reasoning than the problems are intended to develop. Mm-hmm. So I call this the less sophisticated reasoning trap.
Yep.
What do I mean by that? What I mean is kids can get correct answers using that particular algorithm, but they can get away with using less sophisticated reasoning than we should be developing with them if those are the kinds of problems kids are learning to solve.
Yeah, absolutely.
All right, so here's an example. If I were to ask you to solve a multiplication problem and you use the traditional algorithm that's out there, then you could... so it's multiplication. Mm-hmm. So if you think about developing mathematical reasoning, that graphic that I've created, and we want to develop from counting strategies to additive thinking to multiplicative thinking, if we're talking about the multiplication algorithm, we should be developing multiplicative thinking. That's what we're doing, right? You're learning multiplication. You should be reasoning multiplicatively. We need to develop multiplicative reasoning because we build on that to build proportional reasoning, and we need to build multiplicative and proportional reasoning because we build on that to build functional reasoning and other things. Mm-hmm. So if we're doing multiplication, then we need to be building that kind of reasoning. So Kim, If I were to ask you to solve the problem 14 times 21, and you wrote that down with a traditional algorithm, then you might put the 14 on top and the 21 on the bottom. That doesn't really matter. Oh, this is a terrible problem to use as an example. You know what? I actually meant to give you 14 times 19. That would be a much better example.
Okay.
Sorry.
Right.
This is going to be a great podcast, I can tell. Okay. So
maybe, are you asking me to write these steps down?
You know what? I'm going to give you actually a separate one more problem.
Okay.
That you're totally laughing at me.
No.
You don't know. Oh, do you remember the other day when you tried to do the algorithm and you did it wrong? That was hilarious.
Yes.
Yeah, because it's been so long since you've actually done it. All right, 29 times 13 is the one that I'm going to give you.
13. Okay.
Yeah. Okay. So if we were, I'll help you, Kim. It's
okay.
all right. If we were doing the traditional algorithm, then we might
pause for just a second. I can't not think of the problem I want it to be. Like, I'm so ingrained in actually thinking.
Your mathematical brain.
I want it to be something different. Yeah.
Your mathematical brain is mathematizing as we go. And you're like, really? You're going to make me do these dumb steps? Yeah. Yes, I am.
Am I writing down? Am I
20? Yeah, write down 29 and then underneath it, write 13.
Okay.
And then put the little X next to it and draw the line.
Yep, I gotcha.
Okay. So the very first step that we would have students do is do 3 times 9. Or 9 times 3, either one. If I am a student doing the algorithm, do you agree with me that I could now say I need 3 9s or 9 3s? And then I could say, ready, begin. 9 plus 9 is 18, plus another 9 would be 20, 27. Like you could actually skip count to find 3 9s. Or you could take about 9 3s and you could skip count 3, 6, 9. You could literally find 9 3s. So you could get the correct 27 and you could write down the 7 below and put the 2 above. But the whole time you are thinking additively because you're skip counting, not multiplicatively. You could agree that could be true?
For sure.
Cool. Then I'm going to do the next one. And now I'm just supposed to do 3 times 2. So I could go 2, 4, 6. So I could skip count 3 2s, add the 2, write that down correctly. Then the magic 0 or the turtle lays an egg or whatever it is. And then I could do the next row. And I could think about all of those single digit multiplications. I could actually do them additively. So if you can picture the development of mathematical reasoning graphic where I've got counting to additive to multiplicative, I'm supposed to be building multiplicative reasoning, but I'm getting away with using additive reasoning. And I could do that through the entire problem. I could use additive reasoning and then add all the columns of things at the end, and I could get a correct answer. And my teacher could say, yay, you got a correct answer to a multiplication problem. You must be reasoning multiplicatively. When in reality, you were actually reasoning additively the whole time.
Yes.
And that is the less sophisticated reasoning trap. That I'm getting correct answers, looking like I'm reasoning in a certain way, but I'm actually getting away with using less sophisticated reasoning. And to be clear, when I do those columns of additions at the end of the problem, I could actually also do those counting by ones. I could add all of those columns up because it's just single digit plus a single digit. I could count by ones to add those up. So even in the additive part, I could be using counting strategies, less sophisticated reasoning. So I look like I'm an additive multiplicative reasoner because I'm getting this multiplication problem correct, but I'm actually using reasoning in the level before. I've been trapped. My brain has not been encouraged to grapple with the multiplicative relationships, to actually think and reason multiplicatively. I've been allowed to just reason additively, get correct answers. And then when I move on to the next topic, the next year, the next whatever, my brain hasn't grown. I haven't been given the opportunity to, and especially I haven't been encouraged and nudged in the opportunity to reason multiplicatively. That is the sophisticated reasoning trap. All right. What are you thinking right now?
I think that many, many students and many, many grade levels are having this exact trap on a daily basis. Yeah. I mean, I'm picturing being a 3rd, 4th, 5th grade teacher and how many times, I see in these classrooms fingers counting as students are adding columns of digits and skip counting. When you said,
oh, go ahead. Keep going.
When you said 9 times 3 and 3 times 9, I'm remembering like my first year teaching, hoping that kids would skip count by 9s instead of skip counting by 3s and calling that a win.
Yeah, sure. Which is a fine win in third grade when we're very starting to develop multiplication as repeated addition, but we have got to get more sophisticated now. We can't leave kids there. Hey, Kim, when you just said that you can picture a classroom where kids are kind of counting on their fingers or maybe they're skip counting, I can also picture classrooms, well-intended classrooms. It's no blame, right? We're just all helping each other move forward. I can picture classrooms where students are looking at a multiplication table for those very same facts. I would submit that that's using not even additive reasoning. That's using looking up on a table reasoning, which is not the reasoning. What are we supposed to, if we're doing multiplication, we're supposed to be developing multiplicative reasoning. Now we're just having students just like look them up on a table, or a student who types in those single digit facts in a calculator.
Yeah, that's not a less sophisticated reasoning trap. That's a no reasoning trap. And that is the would agree worst. Completely.
Yeah. Let me give you one more no reasoning trap where I have a kid go, oh, let's see. 3 times 9 is like the diamond. If it rolls, then it's 20. Yeah, I'm trying to come up with a rhyme. I don't have a rhyme for 3 times 9.
You don't have a poster?
I mean, I'm sure there's one out there somewhere with a story, whatever. So if it's a story or a rap or a rhyme, if it's a mnemonic, if it's a memory retrieving device, then that's not even reasoning at all. At least skip counting is additive reasoning. Well, I say that skip counting is additive reasoning if you're adding the numbers. If you are singing the skip counting song from what's the PBS multiplication Schoolhouse Rock. Now I'm not knocking Schoolhouse Rock, but I am knocking it if you're pretending that singing all 3, 6, 9, 12, 15, 18. I can't even sing the song anymore. But if that's what you're singing, then you're singing a song. You're not even using additive thinking. So it's like you said, it's not reasoning at all. So not only is it the less sophisticated, no sophisticated reasoning trap? Call it both, maybe. Yeah. What were you gonna say?
I was gonna say that you and I are firmly grounded in the belief that is the job. The job is to build reasoners, not just
because that's what mathers are. Yeah, right. Mathers actually reason mathematically. They don't just mimic. Yeah,
right. So I think for some people who are hearing us say like poster song, like if your belief is the job is to just get answers, then that you might be wondering like, why is that a problem?
Sure. Yeah. And y'all, again, this is not about shaming anybody. This is about like lifting everybody up into real math. I am the poster child of we sang songs and raps and rhymes to memorize stuff because I was convinced that mathing was about squiggling and that there was no shark. It was just like, let's memorize the squiggles in the, if you don't know what I'm talking about with the shark, go listen to last week's episode.
Yeah.
So yeah, what we're trying to do is help everybody realize that the purpose of math class is to build mathematical reasoning. And we can. The good news is we can. Everybody can do more real math than fake mathing, than fake math mimicking. Absolutely. Yeah. All right. So Kim, how could we do a better job with the problem that I gave you earlier? Let's do a quick problem string.
Okay.
All right. So first problem, what is 14 times 10?
140.
All right. And I'm going to record that in a ratio table. So I've just written down 1 to 14, and then I've written down 10 to 140. So if we're thinking about 14s, you told me that 10 of them was 140. So 1 to 14, and then 10 to 140. What if I only wanted 9 of those 14s?
That's going to be one less group than we just had.
Okay.
So I'm going to take 140 and subtract 14, which is 126.
All right. So one less group of 14, 140 minus 14, you got 126. Cool. What if we wanted 20 14s, 20 times 14 or 14 times 20?
I'm going to double the 10 14s.
Okay.
Which was 140. And so now it's 280.
Nice. I'm kind of curious. Totally makes sense that you did that. You got anything else for that one?
For 20?
Yeah.
Yeah, okay. We don't have 2 on the ratio table, sure, but you could do 2 is 28 and then times 10
to get the 20, 280. Okay, cool. Just curious. What if we only wanted 19 14s? 19 times 14. So far we have 20 14s because I know a lot of people are listening to this in their car. So we have 20 14s is 280, but now we only want 19 times 14.
Yeah, so I'm just going to subtract a group of 14 from the 20 that I have there.
Okay.
So 20 groups was 280, so 19 would be 266.
266, nice. And we could talk about that subtraction, but today we're not. All right, cool. What if instead I wanted 21 14s?
That's a lot of 14s. I'm going to add 14 to the 20 14s we already figured out. Okay. So 280 plus 14 is 294.
Cool. So far we've kind of solved a lot of problems. We've gotten 10 14s, 9 14s, 20 14s, 19 14s, 21 14s. So at this point in class, I might have a conversation about like, what kind of pattern do you guys feel like we're playing with here? Can you put some words to kind of, are you feeling like we're playing with something here?
Yeah, I think we're thinking about groups of 14s that we know, like the 10 of them and the 20 of them. And then we're going like a little under or a little over. 19, 21. Once we found the 20 14s, we could back, or once we found the 10 14s, then we could ask you for 9, a little over, a little under. Okay, cool. Next problem. How about we're going to change I'm no longer on a ratio table with 14s. We're going to think about 13s. And this time I'm looking for 30 13s. So I'm going to say I know 3 13s is 39.
Okay.
So 30 13s is 390.
So I've just written down 1 to 13 and then 3 to 39 because 3 13s, like you said, is 39. And then 30 to 390. Okay, cool. So we've got 30 times 13. And then, but Kim, just kind of with the same pattern that we've kind of just been talking about, little over, little under, I actually only want 29 13s.
So I'm going to say 30 13s was 390. So 29 13s is subtract a 13. So 377. So
you think that 377 for 29 13s. And we just sort of went a little over and under. And I don't know if you remember, but that is the problem I finally landed on when we were doing the algorithm earlier. I said 29 times 13.
Yeah.
Where we could skip count our way through that problem. Or use no reasoning if we're just singing a song or using a multiplication table or whatever. Or we could kind of develop this over-under strategy and we could help kids, we could high dose kids with the pattern of, how'd you say it? Using what we know, like a multiple of 10, like you found, well, if I can find 30 13s, bam, I can use that to help me find 29.
So I just, when I said I can't not like think about something that makes sense to me, I was going to do 30 because 29 is so close to 30. I was instantly thinking to myself, 30 13s is 390. So it's going to be around there. And I just want to point out that when we wrote the 29 times 13, like did the 9 times 3 stuff, the first row, row has 87 in it on my paper, which is a partial, but it's not even like the biggest partial. It's nowhere near the 390. So when go ahead. When I wanted to go with 30 times 13, I was like within the ballpark. I was in the hundreds that I was going to be. It's just the idea of magnitude and the idea of reasonableness. I knew that when I landed at 377, that it was near my estimation. And you can't do that when you're starting off with an algorithm and thinking about the
smallest, least consequential numbers first. Absolutely. Yeah. So it was interesting. We just had Jo Bowler on our challenge and she talked about her book Math-ish. And when you said that instantly you thought about 30 13s. And so you knew it was going to be around 390, but it was, you were too high. So it was going to be a little bit lower. You were finding an ish number. You found an ish number. Jo Bowler says, find your ish number first. It's not about this whole other thing to teach kids about approximating or what's the other word I want? Maybe just approximating. Estimating. Yeah. It really is getting kids to kind of like think bigger picture.
And it's also not find the answer of 377 and then round it to 400 or 380 or whatever else to fill in the blank.
Which is totally what I did as a student.
Oh, so many do. Yeah.
Yeah. Well, and if it's all about answers, if the purpose of math class is all about answers, then why not do what I did?
Yeah.
Because I got the correct, I knew I was going to have to get the exact answer anyway. So I might as well just get it and round off. But if the purpose is to develop mathematical reasoning, then all of a sudden finding an ish answer is part of what you're doing. I love that you point out that the very first steps of the algorithm immediately send you to the least consequential part of it. And it doesn't help you ish the answer. It doesn't help you get a sense and a feel kind of for where you're going to end up. But reasoning does. And I'll also say that it's not enough to just tell kids to ish. I think we really do. Most kids need a higher dose of patterns to be able to have something to ish with. I think there's a lot of kids that will look at 29 times 13 and not be sure how to start to estimate. And so then teachers come up with more squiggles to memorize about how to estimate that.
Round this one to the tens, round this one to the hundreds. Wait, how long? Yeah.
Yeah. And we're not about more steps to memorize and mimic. We're really about what are the major relationships that we can high dose kids with, so that they can be thinking and reasoning doing the mental actions that mathematicians actually do. All right. So Kim, the first trap that I think hits all algorithms is that kids could mimic those steps of the algorithm and get correct answers, but actually being trapped in less sophisticated reasoning than the problems are being are there for to help develop. Hey, one other quick thing that I want to mention is that a thing to think about with these algorithms is that every algorithm learned, if the goal is to get answers and I'm learning these steps of algorithms to mimic them, every time I memorize the steps of another algorithm, it's another thing for me to get confused about. It's another thing for kids to go, oh my gosh, I have to memorize another one. I don't know if my brain is going to start leaking out. I only have so much, like I need to cork this ear because it's going to start. There's too much. I'm filling my brain with all this nonsensical sharp dots that aren't connected. And when are we ever going to use this? It's one more thing to get confused about. But every strategy learned makes the next subsequent strategy easier to learn. Because every strategy, not memorized, but strategy developed, every set of major relationships where we actually build those mental maps in kids' heads becomes a more robust map upon which we can build the next strategy.
Yeah,
and it makes,
so good.
Yeah, right? It's so good. Strategy learning, relationship learning is synergistic. And algorithm learning is really just a dead end that traps kids. And less and less kids move on and succeed. Yeah.
Yep. All right, y'all, get the Developing Mathematical Reasoning, Avoiding the Trap of Algorithms out now.
Bam. And y'all, thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. And keep spreading the word that math is figureoutable. Hey, listeners, don't forget, go to mathisfigureoutable.com/book-launch to register for the free Developing Mathematical Reasoning, Avoiding the Trap of Algorithms book launch webinar taking place on March 18th. Y'all, I'm going to be there. It's going to be cool. You do not want to miss this. Totally free. Come join us. mathisfigureoutable.com/book-launch. We'll see you there.